Hello, and welcome to 5 Minute Math. Today we are going to be looking at lessons we can learn from the Algebra 1 STAAR that took place in 2025. We're specifically looking at the readiness standards in which we as a state scored less than 60% accuracy. And we'll start with our most troubling standard, A.11b, and kind of work our way up to our readiness standards that we feel a little bit more comfortable in. So let's start with A.11b, simplifying numeric and algebraic expressions. It's the laws of exponents. And so we really struggle with both of these, right? And so let's take a look first at number 28. You see it is a two-part problem. We've got drag and drop here. And I think there's one thing that kind of stands out to me is it's set up for us visually right here, and you should see 2/6. And so outside of what we do with our exponents, we should take our coefficient and be able to do something with 2/6. And we should be able to say, okay, so 2/6, right? That's going to simplify to 1/3 because 2/6 isn't an answer choice. And so we're going to grab that 1/3. We're going to put that right here. So that's one point that we should already have. Now we have to do something with our x to the 12th over x to the negative third. And so there's two ways that we can kind of attack this. One, we could just keep it to one step, and we could do the quotient of powers, right? So when you're dividing one base by a similar base, you can end up subtracting the exponents, and so it could end up being x to the 12 minus, and then it's a -3 down there. So minus -3 ends up becoming +3, so that equals x to the 15th. Another way to deal with it is the negative exponent. Now, what we end up having right here is 1 over x to the negative third, right? And so when you have that negative third, that becomes 1 over 1 over x to the negative third, and that becomes confusing. What this ends up doing is that flips it up to the top. That just inverts it. And so this becomes x to the third. Now we still have this x to the 12th to deal with, so now we can use the product of powers. X to the third times x to the 12th, that's going to equal x to the 3 plus 12, which gets us back to our 15. So either way, we're looking at it like that. Now take a look at this. Only 24% of our students got both points. 31% of our students got partial credit. I'm thinking that 1/3. We had 45%, almost half of our students not able to get any points. They could not even at least get that 2/6 equals 1/3. So even in problems like this, let's focus on what are the easy things. Can we simplify any of the coefficients without using any product of powers? Can we understand that 2/6 equals 1/3? So what do we have over on number 48? It was more traditional multiple choice, but only 31% of our students got this correct. We have to do something with this -2 first, right? The power of a power. So we need to go ahead and square everything, but take a look, it's a -2. And so we need to go ahead and flip all of this down to our denominator. And so that first step might be something that students struggled with. So this is going to end up becoming 1 over x times y cubed raised to the second power, and then you get that y. Okay, so now we're not adding, we're not doing 3 plus 2, that would be a power, the product of powers. This is power over power. We're going to end up multiplying those. So that's going to be 1 times, now 6 cubed, or 6 squared, excuse me, makes 36. Y the third, and then multiply that by 2, that becomes 3 times 2, that becomes 6. And then we've got this y still just hanging out right there. So we're going to recognize that as y to the 1, and then we can use our product of powers, right? So 1 over 36 y to the 6 plus 1, or y to the 7. And so you notice we got two different options here that are very similar, right? If we forget that extra y, or if we end up adding, if we use the product of powers here, we do 3 plus 2 plus that 1, that gets us that 6. There's a few different ways to kind of get that incorrect answer, but our answer here is going to be A. So that negative exponent in the denominator of 28, that first one, definitely increased that complexity because we know that, right, 2 to the negative 2, right, equals, 1 over 2 to the 2, right? So we kind of know that if it's just a regular exponent and it's to the negative power, we're going to put it in the denominator. But does every student know that if we have something like this, if we have a negative that's already in the denominator, it's going to end up flipping back up to the top. So that is something that we need to speak about with kids. And as I showed you on that first one, right, we could have solved using the quotient of powers. That would have been one step. We could have done a negative exponent, the product of powers. And then for 33% of the students chose B. And so that's the one that we were kind of circling around 33%. That's more than chose the correct answer of 31%. So they got really, really close. Now we can't tell what the misconception is. Either they forgot that extra y, or they used the product of powers rather than the power of power, and they added the 3 plus 2. Either way, there's still some misconceptions there. And we had to apply three rules, right? We had to apply negative exponent, we had to do the power of power, and then we had to do the multiplication of power. And probably the trickiest of all, both problems included negative exponents. So that's the analysis. Now, what does this mean for us? Anytime you see this white text, that means this is kind of a instructional implication. And so I think one thing that we can do to help our students is, especially around this point right here, we need to show how, if applicable, expressions could be simplified using more than one sequence, right? We could have used the quotient of powers, or we could have done the negative exponent. The more we do that, the more we're going to solidify just the common rules, how these things work, and it really just builds conceptual understanding when you can get to the same answer in multiple ways. Next, 8.3D, we are looking at graphing linear inequalities. Now, we always typically do a little bit better on problems like number 10 because we get to just choose from four answers. Whenever we get to graphing it ourselves on number 30, that increases the complexity. All right, so we've got a problem set right up there. We've got 3y minus 2x is less than or equal to negative 6. That's our inequality. We should be able to eliminate two answers immediately because I'm sitting with a less than or equal to. And so that's gone because those are dashed lines. That needs a solid line. Now, I'm looking at A or B, and if I'm looking at it closely, those are the exact same lines. I don't even have to worry about plotting the correct line. Those are the exact same lines on A or B. It's simply the different solution set. Okay, so do I need a shade above or below the line? Well, one thing we can always do is let's just take 0, 0. And so let's see if that needs to be included. So the origin, 3 times 0, and just 0 is easy because it just cancels so much stuff. Less than or equal to negative 6. All right, so that's going to be 0 minus 0, or just simply 0, is less than negative 6. Is 0 less than negative 6? Well, no, if you look at a number line, negative 6 is right there, 0 is here. 0 is actually greater than, which means it is not going to be in the solution set, which means it is going to be A. We're going to go ahead and shave that up there. We can also take a look at it like this. If we want to put it into slope-intercept form, right, we can say 3y less than or equal to negative 6. Let's see, 2x minus 6, right? We can divide by 3. And you can get it like this if you really want to look at it like this. Y equals 2/3 x minus 2. And I misspoke. It's 0 is not a part of it. Therefore, we're going to choose B. We could also just take a look at this sign here. And since it's not a negative x coefficient in front of the y, it wasn't going to flip. Whenever you have a less than or less than or equal to, you're going to shade below the line. So our answer there is B. We had 49% accuracy. It's always going to be a little bit more challenging on something like number 30 because it's blank. You can't use process of elimination like we did on number 10. So First, we need to graph something here, and we're going to graph, we know we're going to graph a dotted line because it's greater than, rather than greater than or equal to. So we need to make sure that we change that to dashed. So I'll draw it for us here, but this isn't interactive. This is just a screenshot. So let's get our y-intercept right there at 3, and they already give us the slope, okay? Slope equals 5. So I'm just going to count up 1, 2, 3, 4, 5, and then over 1. So that's 1. And then 1, 2, 3, 4, 5, and then over 1 up there. And then the other one's going to be down there. All right, so something that looks kind of like this. All right, so there's my line. Now I need to decide which side it's going to uh, be shaded on. And I need to click on this solution set next, above or below. Well, remember, if it's greater than, it's going to be above the line. Now, to verify, let's check 0, 0. This time 0, 0 seems like it might be included. And so let's do 0 is, excuse me, greater than 5 times 0 minus 3. So 0 is greater than negative 3. That is correct. And so my shading is going to go like this because 0, the origin, is included. We had 67% get nothing, not a single thing. Y'all, this is slope-intercept form. We can graph that line. Now, the default is solid, so students might have graphed it, and if they graphed it with solid, they're not going to get a point. You need to get 1 point for graphing it correctly with a dashed line, another point for the solution set. And so this is definitely a little bit more challenging. And so let's look at why students might have made some incorrect choices. Number 10, 22% chose A, not super surprising. That's the correct line. It's just the incorrect solution set. So 49% got it correct, 22%. So you're looking at 71% that at least could get A or B. That's actually not that bad. And um, they could have converted to slope-intercept form. We did that to test it, or they could have just tested 0 as the x and y to graph the equation, or they didn't even necessarily need to graph it because A and B were the exact same line. So sometimes we just make it more trouble than it's worth because we're not using our visual cues. And then we had 2/3, 67% of our students got 0 points on number 30. And this solution set, once again, in order to trigger the shading, after you graph it, right, the default is here. You have to graph it. You have to change the default from solid to dashed if you want it to be dashed. Then you have to select this solution set. If you don't click that, then you're not going to be able to select the solution set. So you might just graph the line and then move on if you're not paying attention. Now, it would give you a warning saying you haven't, answered the question, but it's not the most intuitive. So one thing we can always do, even though we know that greater than or equal to is always going to be above the line, less than or equal to is going to be below the line. When you're taking the STAAR test, you don't want to just use rules. You want to test and just verify if possible, right? So always test the origin, 0, 0, to evaluate whether or not it's going to be in the solution set. That's just a good rule of thumb. And then that graphing tool, there might be some other resources out there that are uh, similar, but I have yet to see them. So if you know one, that's great. But if not, get them on Academy and pull up one of these. Have them go to one of these tests, pull up one of these items. They need to experience how it works. You don't want the very first time they've ever experienced a graphing situation like this to be on the actual STAR test. It's just something that they need a little bit of muscle memory for. Next, we're looking for 8.5c. We're looking for solutions of linear equations. All right, and as you could tell, we did okay on number 11. Look at number 11. Number 11 is set up for substitution. So it's set up just like that. So we're just going to go ahead and plug in that negative 6x plus 2. We're going to put that into the 5. Now we are going to have to use that distributive property to make everything work, which is another big thing we work on in Algebra 1. So that probably was something that they wanted us to do. And so we need to make sure we distribute correctly here, both terms, not just the first term. All right, so I've got a minus 5 minus 6x. And let's just go and make that a positive 30x. Minus 5, positive 2, that's going to be minus 10. All right, so I'm going to add 10 to get that over there, and I'm just going to make that 33x equals 22. And we're going to use our division property. We're just going to make x equals 2/3. All right, if we wanted to verify, we can plug in 2/3 to both of those, and we would end up getting the exact same y is what we'd get, and that would show us our solution. All right, so number 42, or number 24, excuse me, we are looking at two different sets of linear equations, but they're not asking for the answer. They're asking for us to describe it. Now, on either of these, we could graph if we want to, but once again, it looks like we're set up for substitution. So let's go ahead and do that. Let's use substitution. So I'm going to use 3x plus 6. Then I'm going to get my negative 0.5x plus 4 equals 24. All right, distribute. So 3x plus 6 negative 0.5. So it's going to be a minus half of 6 is 3. So 3x plus 6 plus 4, 24. Now look what I end up with. 3x minus 3x goes away. I end up with 24 minus 24. Now, if I don't know how to interpret that, then we're in trouble. I could graph it, and if we graph it, we'll see these lines are exactly on top of each other, which means it has infinitely many solutions. But we can also tell that here, when you get a true statement, 24 equals 24, that means they're infinite. That means it's literally, there's no variables, the lines are on top of each other. If you get something like 0 equals 24, a false statement, that means there's no solution. That's what you would get right there. Okay? And if you get x equals 3, then you're going to get one solution. And you're not going to get something that has two solutions. That's just not possible unless you're dealing with one is a quadratic, one is a linear. That's a possibility because you could end up, graphing like this and get two solutions. That comes more in Algebra 2, though. So we easily could have used substitution for both. And number 24 was a little bit different because we had to describe the solution rather than finding the solution. Now we couldn't because it was infinitely many solutions. So once you saw it, you realize why we had to do that. And then 35% of our students chose B. 35% chose this B. That's more than the exact because what happens most of the time we're doing this? We just get a solution, right? That's the answer most of the time. Or we might have plugged in, let's say x equals 0, right? That's easy. If we're just testing x equals 0, what are we going to get? Well, that's going to go away, and that's going to go away, and we're going to get y equals 4. We're going to get 6y equals 24, and we'll say, hey, look at that. Y equals 4 for both. Boom, one solution. We found one solution, but they didn't test what about x equals 1, x equals 2, x equals 3, x equals 4. It all works. So you can't just test one because that's not going to show you if you have more than one or an infinite number of solutions. So, instructional implications. We need to be familiar with non-traditional statements when using substitution, like 24 equals 24 or false statements, right? What do those statements mean if it's not a y equals or an x equals? Does that mean infinite? Does that mean 0 solutions? And yes, we can graph, and as long as we have a calculator, that can work. But let's consider all strategies because both of these were set up for substitution. So the most efficient, easiest way was to use this substitution simply because they were both, one was in standard form, one was in slope-intercept. If they give you both in standard form, sometimes elimination is going to be the best. But let's evaluate all solutions before we just go straight to graphing. Next, 8.7c, we are looking at graph transformations. We've got quadratic functions here, and we're translating them. Now, What we are looking at typically is we're going to have some type of parent function like this. So f of x equals x squared. It's going to be just your basic quadratic function. And then we're going to end up translating it somehow. Okay. And so we've got some basic translations that we are looking at here. And these are what we typically deal with. So it's going to be, um, so let's go and take a look at this, right? So like g of x equals f of, and then we're going to get this like x, and then we get this minus h, right? And then we get a plus k. Now there's two others. So h and k are really what we mainly deal with. There are two others called in the standard, right? We could end up putting a multiplier on the outside. We can end up putting a multiplier on the inside. That a and the b, they do vertical stretches and horizontal compressions, vertical compressions, right? They just stretch or compress it. But we don't really deal with that nearly as much. Mainly, it's going to be this H and K. These two would not be translations. These would be dilations, right? And then the H and the K are going to be mainly what we deal with. That's just translating it. What really challenges our students is the fact that within this, it's x minus h. So look what I end up with here. I end up with f of x plus 8.7. In order to get f of x plus 8.7, within this format here, it needs to be f of x minus negative 8.7. Since it already starts as a minus, the only way to get it to be a plus is I have to minus a negative, subtract a negative. And so this ends up being x minus negative 8.7, turning into this x plus 8.7. Now my h term, look at this, h and k, does that remind you of anything? This should remind you of the vertex form, so it's all related, okay? So that h is going to be your x value. It goes left and right. And then your k is your y value. It goes up and down. So in this one, it's an x minus negative 8.7, which means my x value is moving everything over to the left. So it's going to be a negative 8.7. It's going to be our answer right here because our x value, these two don't work because they're changing the y value. Only C or D should be considered because we're dealing with the h, and it's negative in order to get that positive 8.7. But you see only 41% of our students get that correct. Number 39, 2-point problem, two different drop downs. We end up having to do both of these. So we have an x minus 6. Now, that's a little bit more normal. If it's x minus 6 and my format is x minus h, then my 6 is simply my h. That ends up being a positive 6 in order for it to be x minus 6. So that means we're going to move 6 units x value to the right. Now the k is a little bit more normal. It's a plus k, which means if it's a plus 2, it goes up. If it's a minus 2, it goes down. The k makes more sense. So that's going to be 2 up. So 2 units up. And that's where we got 36% full credit and 27% partial credit. Now let's take a look at why this was so challenging for our students. They both included this horizontal shift, and it's this x minus 8 that really just makes students struggle because in order to get the f of x plus 8.7, you need to have an f of x minus negative 8.7, and that's just an extra step that's just, it's just confusing for kids, and I understand. For number 12, 30% of our students chose A, and so they didn't even necessarily recognize where it was. The easiest thing to recognize is that K, and so they thought if it's a plus 8.7, we're simply going up. But you notice that within the parentheses is within the x, so that should be your clue that within the parentheses you're dealing with that x value, and you're either going left or right depending on its positive or negative sign. Number 39, that was the second one. It involved both vertical and horizontal, so it was actually a little bit easier to kind of see where the x and the y value were because you had to deal with both, not just one. So instructional implications are down here. It's this horizontal movement, not the most intuitive. We have to spend a lot of time getting students to understand is that x minus h. And honestly, the best way to do that is to graph it. Students could have graphed both of these in Desmos, and they would have seen just literally where those graphs ended up with those translations. And so that's how we can really show students that if you have an x minus 6, it's going to go to the right. If you have an x plus 8.7, it's going to go to the left. They need to see it. So graphing is very important here to solidify what happens. Eventually, we can get into these algebraic rules. And this format, right? Um, this A sometimes is something that we put on the outside to do vertical stretches and compressions, right? But this x minus h plus k, we're going to use that in many other functions, absolute value functions, right? Square root functions. When we get into Algebra 2, this idea of translating a graph based on an x minus h and then a plus k, it gets used over and over and over again. So it gets first introduced here. It's going to become very important for students. Next, 8.2i, we're looking at systems of linear equations. We had two problems on this test, and one of them was pretty easy. You see, number 4, we do have a graph that we could use. On number 34, it was just a verbal description. That was a little bit more challenging. So let's go ahead and take a look at number 4. We need to find two equations here, and so we can find that by using a point, um, this point here that ends up being our solution. So we can use this, right? And if we wanted to, we could plug in 3, 5 into all of these and just find the two that worked. But that is kind of a brute force approach. Another way would be if we can simply find a second point on each line. We can use that 3, 5 since that looks like it's the solutions where they intersect. Let's find a second point and calculate the slope of each line. All right, so it looks like I've got my y-intercept right there on this we'll call it this red line here. That's going to be 2, 0. Or 0, 2, excuse me. And so I'm just going to go ahead and calculate my slope, right? Change in y over change in x. So this is 5 minus 2 over 3 minus 0. So that's going to end up being 3 over 3. All right, so that's just 1. My slope is 1. So it's going to end up being y equals x. And then that literally is my y-intercept. So plus 2. So I see that's here and I see that's here. It's not going to work on C or D because if I solve for y, get it out of that standard form, it's going to end up being a negative x. And I don't need a negative x. I need a positive x because it is a positive slope. It goes up from left to right. Now I need a second point for this other. Looks like it almost crosses the x-axis at 4, but not quite. It looks like it goes right there through 4, 1. And so we're going to use that, and we'll do our same thing. So m equals, and then we will have 5 minus 1 over 3 minus 4. So that's going to end up being negative 4 because it's 4 over negative 1. So that makes sense. Those are both negative 4s. That doesn't help me. I need to figure out the y-intercept. So what that means is I need to go ahead and plug a point back in. Let's just go ahead and plug this solution back in, right? So we need y equals mx plus b. I'll do that right here. My m is going to be negative 4, and let's plug in the 3, 5. Okay, so 5 equals negative 4 times 3 plus b. We also could have plugged in the 1, 4 if we want to. So 5 equals negative 12 plus b. So if I add 12 to both sides, I'm going to end up getting 17. All right, so there we go. B's are 17. So y equals negative 4x plus 17. There we go. 66% of our students got that. Not too much of a challenge. It was number 34 because, as you see here, it's just a verbal description. And it's going to be a little bit challenging. We have to go all the way back to 4th grade to the first time we used the formula for perimeter of a rectangle. So we have perimeter of a rectangle. See this right here is 48. So P equals 48. Okay, the length of the garden Y is 6 meters more than twice the width of X. You see how that can confuse people? Okay, so we can say here's my X and here's my Y. And that length is 6 meters more. Okay, so 6 plus twice the width of X. All right, so if I take my width x, double it, and add 6, I get my y. So that's going to be one of my equations. Y equals 6 plus 2x. I need a second one. And I've got that y equals 6 plus 2x here, y equals 6 plus 2x there. That's not going to work on either of these. Where do I get my second equation? Well, remember our perimeter formula is P equals double the length plus double the width. So I'm going to end up needing my x and my y, so I need my P equals 2x plus 2y, and it's not just P, they give us the value. It's 48. So I've got my double the length, double the width equals my 48. There's my answer. Only 34% of our students got that correct. So we could have used substitution, like I said, at number 4. If you want to take your um, solution of 3, 5 and plug it into all of those, yeah, you eventually would have found the correct answer. And so we didn't have that option on number 34. We had to decipher using the formula for perimeter and the verbal description. And it's that formula for perimeter that probably threw us off because we're not going to see that on the reference materials. That is theoretically already memorized by students, right? We're not in the 4th grade anymore, so we don't have that formula given to us. We need to memorize that. So the description of the second equation, y is 6 more than twice the width of x, that's where the challenge comes in. This is where we need students to have some practice with y is, right? That is equals 6 more means 6 plus twice x. It's right there, but we just need practice getting that from the words into an algebraic representation. And 39% of our students got really close. They chose B. They did all this work. That's actually more than the correct answer. They just didn't double the length and width. They got that y equals 2x plus 6. They didn't remember the correct formula for perimeter, and they didn't double the length and double the width. That was the challenge. So definitely generating equations from verbal descriptions, that is more challenging. It increases the rigor rather than simply using what you see on the graph. And anytime we want to utilize equations from geometric situations like area, perimeter, volume, that's going to challenge students, especially if it's the area of, like of a triangle or a trapezoid that's already a little bit more complicated. That's going to make it more challenging for students. Next, 8.5a. We are solving linear equations in one variable, and the key here is the distributive property. And so let's take a look at number 59. It was not nearly as difficult because even though, yes, there are fractions, we only have to distribute one time. So let's go ahead and do that. 4/3 z. And I'm going to put that little line on my z just because I don't want it to look like a 2. Sometimes our z's end up looking like 2's. So this is going to be -4 times 1/6 z. So that's going to be -4/6 z. Then I also need that -4 times the +9. So that's going to be -4 plus 9. That's going to be a -36. So let's go ahead and take away 36. Now this looks like, oh my goodness, look at all these fractions. It's not as bad as it seems because if I look at my -4/6, that's really just 2/3. If I go ahead and simplify this, so I've got -2/3. Let me go ahead and add 2/3 z to both sides so I can get my z's together. And if we add 2/3 z to the 4/3 z, I end up getting 6/3 z. That's just 2. Fractions are gone. Plus 6 equals -36. Let's go ahead and subtract 6 from both sides. And I'm going to get 2z equals -42. Divide by 2, that's going to equal -21. So that's our answer there. Looked a bit rough, but finally got those fractions out of here. Now, 46, we've got these fraction situations, and students might have come up on this and had no idea how to approach this. Because if you see a number in the denominator, you multiply it by that. But if I multiply both sides by 5, that's going to work on the left, but not on the right. If I multiply both sides by 2, that's going to work on the right, not on the left. Well, you need to do both. Take 5 and 2, multiply them together. What do you get? 10? That's what we end up multiplying both sides by. Ends up making it bigger than you need to, but you actually end up getting rid of both denominators. And that is your first goal. Get rid of the denominators. So if I simplify here, right, 10 and 5, that leaves 1 and 2. If I simplify here, 10 and 2, that leaves 1 and 5. That's my goal, is to get a denominator of 1 so I can get rid of it. Now I'm going to end up needing to distribute 2 into the v minus 6, and then 5 into the v plus 10. So it's the distributive property, but twice. So that's the challenge. That's twice the opportunity to make a mistake. So this ends up being 2v minus 2 and minus 6 minus 12. 5v plus 5 times 10, 50. Now we're normal. Let's just go ahead and isolate our variable. So that's going to be negative 12 equals 3v plus 50. Subtract 50. We're going to get negative 62 equals 3v divided by 3. And you get this really random negative 62 thirds, but it's there. That's our answer. So the fractions really might have increased the difficulty here for students. That's always a little bit more. You could use the calculator, but even then, sometimes it doesn't help. So we need to use just our basic knowledge of operations rather than plugging everything into the calculator here and eliminating the different denominators here. Once we get a few practice items of just finding the least common multiple of both of those, or you can find the number that the smallest number that includes both of those as a factor, like that would work. But we need practice with that because a lot of times students aren't messing with that much. Not in Algebra 1. It becomes a little bit more when we're dealing with, rational or radical equations in Algebra 2. We do that a lot more, but not so much in Algebra 1. And then once we got rid of those denominators, number 46, we have to distribute twice. So that just makes it more challenging. So 30% on number 46 chose B. Let's look at that. You can get this if you only distribute the first term. So if you get all the way to here and then you veer off and you go incorrect, you do 2v minus 6. You notice how I just distributed the first term? And then 5v plus 10. You see how I just distributed the first term right here incorrectly? Well, then you end up getting 3v minus 16, and you see how you get 16 thirds. So we had 30% of our students get that. They got this, and then they still distributed wrong. So it's that distributive property. That's why it is its own entire standard, and it's a readiness standard. Students still need practice using the distributive property. So instructional implications. We need to spend time simplifying fractions on both sides with different denominators. Basically, take a look at number 46 and just generate additional practice problems with that so they can immediately identify, oh, I'd multiply by 10. Multiply, if you have denominators of 7 and 3, multiply by 21. Let's get some practice on that. And then obviously we didn't do it here, but students can always use substitution to verify the solution. If they come up with something random, they're not sure that it works, take that solution, put it back into the original equation, and see if it is true. Next, we're looking at the domain and range of quadratic functions. This is 8.6a. We had two items, and the one that we struggled more with was number 5. There's no visual there for us to look at. We have to find the range of the set of all real numbers that is equal to or greater than or equal to -1. So if we were to just take a look at the clues given us, since we're talking greater than, that means the range, which is our vertical up and down, since it's greater than it, that means it's going to open up. And so we're looking for, we don't know what the horizontal shift may be, but we're looking for something that's going to open up and it's going to have its vertex right there. Don't know what the x value is. Let's think it's 1 or at 0, but the y value is going to be at -1, right? That's what we know from here. So we could go ahead and eliminate two answers immediately because we have got these two, C and D, in vertex form, right? So we've got the x minus h squared plus k, where your vertex is 8 and k. And so what we see here is that our h is going to be -3. We're not really worried about the h, so let's not even worry about that. Let's just focus on our k, right? So this is going to be a +1, so that's already in the wrong spot. It needs to be -1, and you're always looking to see what is our multiplier on the outside. If it's negative, it's going to open down. We want one that's going to open up. Okay, so that's got a vertex at +1 and it opens up, so that's at the wrong spot. This has got a vertex at -17, okay, and that opens up at the wrong spot. At least it opens up, but it starts at the wrong spot. It's at -17, so much too low. So we're already done with C and D. So we've got two left, okay? It could possibly be B. We don't know until we put it into vertex form or we graph it. But you know what? I can tell you it's going to be B because take a look at this. We have a negative x squared, right? So we do have this -1, but that negative means it opens down. So without graphing, which you can either complete the square, put it into vertex form, or you can just put all of these on the Desmos and graph these to figure it out, right? Our answer is B without any type of calculation. We're just using what we know about quadratics to eliminate incorrect answer choices. And that is the correct answer. We did a little bit better on 32 because we're just interpreting this graph. Now we're looking for the domain. So that means we're going left and right. And we're looking at, we see that it is closed. So it's going to be all real numbers less than or equal to, it's closed, I'm going to include that, and we're at the 5. Okay, so all real numbers less than or equal to 5. So that would be our answer on that one. And we did fairly well on that, 60%. So there's no visual support for number 5. We could graph it, we could change everything into the vertex form, or we could just use the clues like I showed you. 33% chose A. So just immediately this -1 is sitting right there, and that -1 is fine for the vertex. It's this negative symbol out front that's going to make it open down rather than open up. And so we had 33%, almost as many students choose that. And they probably saw that and said, oh, this is so easy, I don't need to graph, which is why they had that as a distractor to try to tempt kids to not look at any of the other chances or any of the other choices. Because -1 obviously doesn't show up anywhere there. So visually, there's nothing about that that says it's going to have a vertex at -1, but it's not in vertex form, so we wouldn't expect it to. And we've got a truncated graph on number 32. Didn't cause much confusion. So what are some of our instructional implications? Well, like I walked you through, how could we identify features of quadratic functions without graphing, right? What can we tell about a graph if it's in the vertex form? What can we tell about a graph if we know that its coefficient or leading coefficient is positive or negative? There's quite a few clues. Now, if I wasn't able to eliminate A like I did here, eventually we'll have to graph this or we'll have to put it in the vertex form. I was able to eliminate 3 out of the 4 answers. But sometimes you can eliminate 2 answer choices immediately just because of some of these features of the quadratic equation. And it's the sign of the leading coefficient, right? That's one that sometimes our students tend to forget. We need to repeat that we can go ahead and do this. So perhaps we might give students a series of equations and say, I want you to solve this um, without graphing. Can you find the vertex of such and such without graphing and force them to do it without just plugging it into Desmos? Next, we're looking at A.2a. We had 53% overall mastery, domain and range, but this time of linear functions. So domain and range still tends to be a challenge for quadratics, for linear functions. And so we see that the one we struggled with a little bit more was 48, and it's because, look, it says right here, in the standard, continuous and discrete. All right, so you can buy at most 4 tickets. We need to find the range. There's no X and Y. But we do need to know that we are dealing with our X and our Y. It's going to be given to you in this format and where your independent variable is going to be on the left. In this case, it's called P. And our dependent variable, which is our range, is going to be on the right. In this case, it's called C. Now, we've got 4 values here, and our answer is going to be those 4 values. And you would think, oh, that's pretty easy, but look, we also have that. So the challenge here is recognizing that we're dealing with an amusement park and we're purchasing tickets for an amusement park. So you can't buy half a ticket, you can't buy a quarter of a ticket, you can't buy a third of a ticket. You buy a whole ticket, which means we're dealing with discrete data, not continuous. And so one of our most chosen incorrect answers is going to be that continuous data, because that is going to be what we're typically dealing with linear functions, but not always in real world situations. So we had a little bit less of a challenge on number 37. We're looking for the domain. We have the graph. I mean, the domain is literally going to be the x values, and it runs from 0 to 10. So you notice we've got both of these that run from 0 to 10, but one of them has an x, one of them has a y. So we need this x value. And then over here on C, we're dealing with what the range would possibly be. So not as much of a challenge on number 37 as we did on 16. So we had discrete and continuous data. We had 31% choose B. And that's, I mean, you put that together with 48%. Now we're looking at 79, almost 80% of our students getting this with at least identifying the range here. But the challenge is not identifying the range. The challenge is it continuous or is it discrete? So sometimes we get so focused on identifying the domain versus the range, we don't spend enough time deliberating whether it should be continuous data or discrete data. And then for number 37, we had 25% of our students choose C, and that's the range. I mean, it's listed right there as the domain is what we're looking for, but some students are still focusing on the range rather than the domain when they need to be looking at just one or the other. And so that's just a continuous challenge. So we need to identify domain or range. Then we have to identify, is it continuous or discrete? So there's really 2 parts that we need to focus on. So we need to continue to equate the domain with the x axis, the x variable, and the independent variable. The range goes with the y. The range is the dependent variable. We just need to continue to use those terms independently because especially like we saw here on number 16, there is no x or y. They had p and c. So we had to kind of go back to 6th grade to think about what was our independent and what is our dependent variable. And we need to have them to just have them describe scenarios, just real world scenarios. They don't even have to solve anything. Where would discrete data be more appropriate than continuous data, such as buying tickets for an amusement park or buying televisions at the store, right? You're not going to buy half a television. If they can start to identify some situations in which discrete would be better than continuous, that's going to help them with that differentiation when they need to do it on the STAAR test. Next, we are writing exponential functions. This is 8.9c. And as you can tell, we did pretty well on number 18. It was number 47 we struggled with. So on number 18, we have just the table of values, and we need to find which equation best represents that. Now, when we're looking at our reference materials, we never get our standard form. We have it for y equals mx plus b. For linear equations, we have our slope-intercept form. We have our basic quadratics, but we don't have anything for our exponentials. So we need to know that we're looking for y equals a times b to the x, and we simply need to know what this a and this b stands for. So the a term is going to be our initial value, or what happens when x equals 0. Because if x equals 0, then that means we're dealing with b to the 0. Anything to the 0 is 1. Therefore, when you're multiplying by 1, it's just the identity property that goes away. So y equals a when x equals 0. And so when x equals 0, we actually have it right here. We've got it as 90. So therefore, that's our initial value. That is our y-intercept. And so we need to look at either B or C. Now, we don't necessarily need to do any type of calculation to figure out whether it's B or C, because the next thing we need to look at is our B, which is our rate. And as you can see, as our x is increasing, what's happening to our P of x, or our dependent variable? Well, it's decreasing, which means it needs to be less than 1 It's a decay rate, and so only C is going to be less than 1. Now, if they were two different versions of that B that were less than 1 and you needed to calculate, right, you can always find it by just taking the ratio of each P of X term by the previous P of X term. So 90 over the previous P of X term, 270, is the same as 30 over the previous term, is the same as this over the previous term, and you can see we're all going to equal 1/3. So that's our answer there, C. Now on number 47, we're needing to take a real world situation, what we call a verbal description, and then put it into the same A times B to the X. Okay, so we see when we say we open a money market account with $2,500, okay, that's going to be our initial value. So we're going to say A to the T, right? That's going to be our dependent variable equals our initial value of $2,500 because that's what we're opening with. That's our deposit. And so we've got that in each of those, though the formatting is a little bit different in C. And look what's happening with D. You notice that T is not in the exponent form, they're just multiplying. So that's not even in the right format either. Now what we need is we need a rate. Okay, so what is our rate? It's going to increase by 0.5%. Okay, so the increase is going to be 1 plus the R. This is what we're dealing with compound interest. We're going to raise it to the T. So what is our rate? 0.5%. That is not the same as 5%. Okay, so 0.5%. Remember, when we take the percent, right, we're going to move the decimal over twice because percent means per 100. So really, we're dealing with 0.005. So 0.5% is the same as 5 thousandths, because this is the same as zero point 0.5 over 100. So if you multiply by tens, right, you're going to get 5 thousandths, which is what we got right here. Now we're going to add that to 1 because that 1 keeps the initial deposit there. And so we're going to end up with the 1.005. And so we get this as B as our correct answer. And we only had 41% of our students get that. So we had less difficulty with calculating. Interpreting is always a little bit more challenging. And so you notice that there's two different versions here, right? Number 18 has to do with mathematical situations, and then number 47 had to do with real world situations. And so those two different breakouts are going to give us different results. We need to practice both. And so that A term was evident in both problems. In the first problem, number 18, we had an x equals 0, so that was there. And then whenever you're doing any type of deposit or interest or anything like that to do with banking, they're probably going to give you the initial principal amount. And 33%, the problem was not identifying the initial amount. 33% of students on number 47 chose A. They simply took this 0.5 and they translated it down there. And that's a misinterpretation of you need 1 plus your rate. And then even if you did that, 1.5 is not an option. You needed to understand that 0.5% is the same as 5 thousandths, not 5%. That's 5/10ths of a percent, and a percent is already out of 100. So that's a challenge there as well. We did not necessarily mention exponential. We did not mention compound interest on number 47. Look, any of those key terms that we would look at, right? It just says interest, and it doesn't necessarily say that we are doing compound interest, does not say exponential. So that term needs to be implied there. It's not even uh, explicitly an exponential problem. So we need to reinforce the standard form that's not on any of the reference materials, y equals a times b to the x. And then we need to find this b rate of 1 plus that interest rate. And if it's a decay rate, then it would be 1 plus a negative, and it would end up being less than 1, right? So a growth rate is going to be greater than 1. A decay rate is going to be less than 1. And then it wouldn't hurt to go ahead and review the difference between here. Those are not equal. Okay, 0.5% is not equal to 0.5. And that's something that it would not hurt to review with students because they might get all the way up to the very end and then choose the wrong rate. Next, 8.8a, we are looking at quadratic equations and we can solve it with a multitude of options, factoring, square roots, completing the square, applying the quadratic formula. So we have number 26, and they give it to us right here, right? So they give us this equation. We can find the width, x of a rectangular deck. It has an area. We need to find the width. Well, the width is x. We need to solve for x. So we don't really need all of this context of length times width and an area and a rectangle and all of that. Because if we factor this out, we're going to get x squared plus 3x. And then we have that equals 108. Well, if we subtract 108 from both sides, we're going to get minus 108 equals 0. Now it looks like a quadratic that we can deal with. Now, how are we going to get to 108? Well, we need two factors that multiply to 108 and add to 3. And so that's going to be 9 and 12. It needs to be a positive 3, so I'm going to do x plus 12, x minus 9. That will get me a negative 108 in the C term. It'll give me a positive 3 in the B term. Now I need to use the zero product property, and I need to do x plus 12 equals 0. If I subtract 12 from both sides, I'm going to get x equals negative 12. Then I need to do it with this other term, x minus 9 is 0. Add 9 to both sides, right? And you're going to get x equals 9. Now, we can only have one of these because this is a real world situation. You cannot have a negative length, so it can't be negative 12 and positive 9. It can only be positive 9. Because sometimes when you're dealing with quadratics, when you interpret it into a situation, you don't take both solutions. And you can't have a negative 12 length. You can't have a 9 length, so that's going to be our answer, C. And then this isn't in your standard quadratic form, and we don't need it to be because look, we're taking this 2x plus 1 and we're squaring it, right? So the easiest thing is, well, let's just take the square root of both sides. And we already have a perfect square on the right side. It's 25. So if we take the square root of 2x plus 1, well, the square root of and then the squared, they're inverses. So I'm just going to get 2x plus 1. Now over on this side, I do need to keep that as plus or minus 5. Because if I square 5, I'm going to get 25. But if I square negative 5, I also get 25 because two negatives make a positive. So when you take the square root of an integer, right, you need to take the positive and the negative root. Now we need to go and split this out. So we're going to get 2x plus 1 equals 5. And then we're going to get 2x plus 1 equals negative 5. So let's take each of those separately. Now I can get my two solutions. All right, so we're going to subtract 1 from both sides. 2x equals 4. So x equals 2. So let's put a 2 right there. And then I'm going to subtract 1 from both sides. I'm going to get 2x equals negative 6. So then x is going to equal negative 3. There's my other answer. Now you could put those in either position. They would accept the negative 3 on the top and the 2 on the bottom if you need to. And you see we had only 34% get both of those items correct. So neither one of these was given in just your standard form of y equals a times x squared plus bx plus c. So we needed to do a little bit of work to realize, and obviously the key is to look at that exponent and make sure if we see that squared as an opportunity, especially in that second problem, we see this as a quadratic, but it's not even evident in the first one. We had to know that if you multiply x times x, you're going to get x squared. If not, we're not getting any signals that we're dealing with quadratics here. So we had to do a little bit of work to even understand we're dealing with quadratics in the first problem. We had to distribute at x, interpret the solutions, right? We only took the positive solution for number 26. For number 36, I had to take the square root and consider both positive and negative solutions. So we want students to solve equations, these are instructional implications, using at least two methods at a minimum. Go back and let's look at what we have in this standard. We have factoring, we have taking square roots, we have completing the square, we have applying the quadratic formula. Unfortunately, what happens is a lot of times students will just use their one favorite method that makes the most sense. They might really like factoring because they're good at multiplication, or they might like the quadratic formula. It's kind of cumbersome, but it works every single time. But these problems didn't necessarily work with the quadratic formula. We needed to factor one, we needed to take the square root of the other. So we need to make sure our students are fluent in more than just their favorite method, because you never know when a problem is going to set itself up for a particular solution strategy. And that's the second instructional implication. Rather than solving every single time, it might be worth it to have a discussion with students where they evaluate a series of problems and then identify what would be the most efficient strategy. Oh, I think factoring would work here because, or we should just take the square root here because, or this one looks kind of off. Let's just take the quadratic formula because there's no clear factors, and I think our answers might might include radicals. Having those conversations with students, having them explain, will just give them additional tools in their tool belt when they come across these problems on the STAAR test. Next, 8.3b, we are calculating the rate of change in linear functions, and they can come in tables, they can come in graphs, they can come in equations, they can be in real world problems, they can be in mathematical problems. So rate of change is huge. So first off, number 13 looks pretty straightforward, but look, we only had 48% get this correct. And it's this right here. Which value represents the rate of change of y with respect to x? So if you are not familiar with that terminology, y with respect to. So y, and then with respect to means we're going to divide. So y over x. Does that look familiar? Well, yes. We're looking for our constant, our direct variation. We could call this the slope. Basically, we're looking for our slope or our rate of change, but it's the vocabulary, y with respect to x, that's probably tripping them up because they're not really sure what's happening, and there's a whole bunch of sevens over in our answers. So basically, we need to solve for y, right? We need to get this y with respect to x. And so we're going to go ahead and take our x plus 7y equals negative 14. And let's go ahead and get our x on this side, right? And so we're going to end up with 7y equals negative x minus 14, divided by 7. That gets rid of that. We don't really need to do anything with that, that negative 2, that b term right here. But what is that rate of change with y with respect to x? Well, what we have here is negative x over 7. Now we have to interpret this to understand that negative x over 7 is the same as negative 1x over 7 is the same as negative 1/7 x. So you see we had, even if we were able to get that negative x over 7, we still had to do a little bit of work to interpret that as our negative 1/7. And we only had 48% of our students get that correct. There were just a whole bunch of sevens here. And if you didn't know what to do, you were probably just guessing. Now, looking at number 50, it was a little bit more clear cut because we have a graph and we're looking at the rate of change. And we see the same thing, distance from home in miles with respect to. So that language should be something that we refer to. And look at this, distance from home in miles. Okay, so here's my distance from home in miles. So that is my y value. With respect to the time in minutes is my x. So there it is again, it's y over x. And so we're looking for this rate of change, and we can look at the rise over run if we want to. So there's obviously a point right there, and we can use this point right here if we want to, right? So what is our rise? Well, it's going to go down 6, and then it's going to go over 8. So negative 6/8, which is a negative 3/4. So a decrease of, and that we need to interpret the negative as a decrease, and it's negative 3/4. If you got 4/3, you just flipped and you did x over y. So those are our two answers there. Now, students might have been familiar with this formal language, this rate of change, y with respect to x. It was also in number 50, but at least they used the terms that were on the x and y axis, and they could, if they needed to, they could use those as clues. But we need to use that language there. And 21% chose A, 21% percent chose B on number 13. So 21%, 21%. And why do you think they focus on 21%? Well, there's only one coefficient here. It's that 7. And they figured it's got to be positive or negative 7. If they didn't know what to do, they just went with a 7. And obviously, with this in standard form, not in slope-intercept form, 7's not even an answer. That graphical representation number 50 did provide some additional scaffolding. They could do what I did, and they could just count the rise over the run. But 20% chose B, and this is the decrease, but they did X over Y rather than Y over X. And so I mean, between those two, that's 84% that at least recognize that's a decrease because look, increase means positive. We should have been able to immediately eliminate that, but about 16% of our students still had difficulty even eliminating those two answer choices. So let's go back into our direct variation, k equals y over x. Let's use this formal language, y with respect to x, or if it's in context, right? Distance from home in miles with respect to. If we use that again and again and again, that will just trigger this idea that, oh, we're dealing with our rate of change, and we know how to calculate for rate of change. Next, 8.9d, we're graphing exponential functions. Now, number 33 was the challenge. We can look at number 2 real quick. Look at that. 79% correct. That is fantastic. But we are simply identifying a key feature, right? So this particular standard is packed because if you're graphing exponential functions, that's hard. That's what we're doing right here. If you are identifying key features, y-intercept and asymptote, that's fairly easy. That's what we're doing on number 2. So the equation of the asymptote is x equals 4. No, that's a vertical line of x equals 4, right? That's not going to work. The function is increasing. It's not increasing. Look, it's decreasing. It's going down. So that's incorrect. The x-intercept, there is no x-intercept, right? On these basic exponential functions we deal with in Algebra 1, there's always an asymptote of y equals 0. When you get into Algebra 2, we start shifting the exponential up and down so that the asymptote starts shifting up and down through translations. So that's not correct. And what do we have? We have a y-intercept of 0, 3. It's right there, right in front of your eyeballs. So we do have this is our correct answer, and that was not difficult, right? Almost 4/5 of our students got that correct. Number 33 was challenging because they have never seen a problem like this. I did not even know this was a feature of Cambium, that you could graph quadratics, that you could graph exponentials. We are used to graphing linear functions. So first we had to recognize this was an exponential. We had to select 2 points, and then it did the graph for us. So if we're not used to just graphing like this, how in the world am I supposed to select 2 points? Well, we need to select 2 x values, and this is what I suggest to make it easy, right? Let's select our x of 0 and our x of 1. Now, our x of 0 is going to be our y-intercept. So what ends up happening is we say 6 times 1/3 to the 0. Well, anything to the 0 power we need to know is 1. So that's going to be 6 times 1, which equals 6. So my first point should be fairly easy. And we didn't even really need to calculate that because that a term is always going to be your y-intercept. So we've got 1 point there. Then we needed to find another point. That might have been a challenge, but I would suggest using 1. And so let's look at it like this. So let's do a different color here. So we're going to do 6 times 1/3 to the first power. Anything to the first power is just itself. So 6 times 1/3 equals 6/3 equals 2. All right, I can graph that. So that's 1 comma 2, and we've got that. If you were able to select those 2 points, the graph would just automatically emerge, and it's going to come like this. But in order to do that, you had to first select exponential, then you had to come up with your 2 points. And it was a 1 point problem. We either got it or we didn't. That was extremely challenging, and that's a new feature that probably threw our kids for a loop. We didn't have much problem in number 2. We've never been asked to graph an exponential function on STAAR before. Instead, it was identify the correct exponential function. But graphing it is new. So we had to first select the correct graph between linear, quadratic, exponential. We had to identify the new points. Like I said, I suggest going x equals 0, x equals 2, and then graph it correctly. So what can we do in our classroom? Well, we can always graph on paper given a table of values or an equation. And I would suggest give them the equation because that's what they had to do. So give them an equation, have them select 2 points, and if they could just do those 2 points, the graph will graph itself. But ultimately, I suggest we get our kids on Cambium. These tests are open and released, and we get to that number. Unfortunately, it's number 33, so they're going to have to kind of click through the first 32 problems of the test to get there, but they need practice graphing. They need to see it, touch it, feel it, smell it, taste it. Because if not, it's going to surprise them when they get there. There might be some other third-party resources that mimic that, but unless it's exactly like what they're doing on Cambium, I suggest we get onto it, practice it, and just have them graph different functions. And they within that, once they have that tool, you can give them different equations. And you can say, all right, now graph 6 times 1/2 to the x, or 3 times 1/3 to the x. Have them graph a few different exponential functions so they get the feel for it. And then we have a point 10e. We are factoring trinomials, and we need to find number 20 is just giving us one factor. Now, this is going to be quite a bit harder than number 44 because if you're only given one factor, I actually have to do the work. I can't just reverse engineer it. If you take a look at 44, which let's go ahead and start with 44, I don't actually have to factor this. If I really want to, I can distribute all of this and I can reverse engineer and see which of these, right? I can use FOIL and I can use the distributive property to try to find which of these actually come up to us. Now, that's not the best way to do it, right? Let's go ahead and divide each of these by 3 to get our first term. And so if we divide each of these by 3, that's going to be 3. And then we're going to get 6/3, which is 2, plus 3/3, which is 1, minus 9/3, which is 3. Okay, so I've got this one right here, 3 times 2x. Okay, so we've got that right there. Now I need to go ahead and just keep that 3, and then I need to go ahead and factor, right? So I need to have a 2x, because that's the only way to get that a term is the 2. And then I'm going to have one positive, one negative. No, the only way to get to 3 is a 3 and a 1, but I do need it to be a positive x, which means I'm going to need a positive 3 right here and a minus 1 right here, because what that gets me is a negative 2x plus 3x. And then that gets me my positive x in my b term. So then this gets me 2x plus 3, x minus 1. All right, so those are our answers. We did okay with that because even if I didn't do that, I could literally take each of these and I could multiply them out. And honestly, I know that's wrong because it's not going to be a negative 3. And I know that's wrong because it's not going to be a negative 3 because look at my leading coefficient. It's a positive 6. So outside of that, then I'm pretty good because process of elimination, that has to be the correct answer. And I have to choose between one of those two because you can't have both of those two be correct, right? So I can say, well, then this term has to be correct. And then now I've just got to choose between those two. Like there's a way I can do this with just process of elimination. You can't do any of that with number 20 because they only give you one, which means you have to do the work. So common factor here. Let's get rid of 5 to make everything easier. Okay, so we're gonna factor out my 5. And so 5 over 5 is 1, so that's just going to be x squared. 30 over 5 is 6. And then 80 over 5, that's going to be, let's see, 36, 16. Okay, so I had to get into 50 and 30. All right, so we're going to get that. Now, we're going to leave this 5 on the outside. I'm going to get x, one's going to be a positive, one's going to be a negative because I end up with a negative c term. How do I get to 16? I can get to 8 and 2. I need it to be negative 8 and a positive 2 because my b term is negative 6. Minus 8 plus 2 gets me 6. So which of these works? Well, it's not 5, so I'm looking at either x plus 2 or x minus 8. And then you see our x minus 8, x plus 2 is not an option. But you see how that's harder? Because I have to do the work. Only 41% of our students get that correct. And so I couldn't reverse engineer the correct answer, like I said, in number 20. On 34% of our students chose B. So they got really, really close, and then they just ended up with a sign error, right? They knew it needed to be an 8 and a 2, but they had that sign error, and that's 34%. That's almost as much as chose the correct answer. And look at number 44. 90% of our students almost got at least 1 point, right? 89% got either full credit or partial credit because this is a lot easier, being able to reverse engineer. So, how do we increase the challenge to make our students really do the factoring instead of reverse engineering? Well, remove all the answer choices, make them just do it on their own. Or if you want them to practice like you would on STAR, only show one factor. Eliminate answering by just using the distributive property. And for both of these, look what we needed to do. We needed to factor out either a 3 or a 5 to make it simple. And in this case, we actually had to factor out the 3 to find an equivalent expression. So let's make sure that we have some leading coefficients that can be factored out because that increases a step that we need our students to make in order to really master the standard.